Today we finally talk about linear systems. So let's start. A linear system like the one in the picture is simply a collection of linear equations. More precisely, we see that in the picture we have n equations in m variables x1, x2, and so on until xm. When we don't have too many variables, then we can just use x, y, z, sometimes w. The coefficients of each variable, here denoted as a11, a12, and so on, as well as the constant terms b1, b2, and so on until bn, are real numbers, or complex if you prefer. Don't forget that by linear equations, we mean that each variable appears in each equation with degree 1. The theory of linear systems can now be studied with very useful techniques, which will help you in avoiding too many computations. However, before studying those techniques, let's recall how to solve a linear system in the most straightforward way. Here, the equations are 2x plus 3y equal to -1, the red equation, and x minus y equal to 7, the blue equation. From the blue one, we isolate the variable x, which is equal to 7 plus y, simply transporting minus y to the right side of the equality. Then we replace the value that we obtained for x into the first equation, the red one, and we obtain 2 times the value of x, which is 7 plus y, and then we copy the rest of the red equation, plus 3y equal to -1. Now we change the color of the equation because we actually obtained a new one, colored in purple, where 14 plus 2y comes from what before, in the previous equation, was 2 times 7 plus y in brackets. Now, 2y plus 3y is 5y, and the constant terms give rise to equal -15. We divide both sides by 5, and we obtain y equal to -3. We now only need to find the value of x. It is sufficient to remember the blue equation, x minus y equal to 7, and the value that we just found for y, that is -3. Now all we have to do is to replace -3 in the blue equation. Then we obtain x minus -3 equal to 7. That is x equal to 7 minus 3, which is equal to 4. That's it. The solution of our first system is x equal to 4 and y equal to -3. Too easy? So let's spice things up a bit. Let's come back to our original picture of the general system of n linear equations in m variables. A solution for this system is nothing but a m-tuple of real numbers, alpha 1, alpha 2, alpha 3, and so on until alpha m, which are a solution for each of the n equations of the system. Now be careful, because a solution may not exist. And even when it exists, it may not be unique. Now we are doing the first steps in order to obtain a general method to solve linear systems, a bit more complicated than the previous one. So what we are showing today is a list of 3 operations that you have the right to do on the equations without affecting the set of solutions of the system. The first is the easiest, interchanging 2 equations. Okay, that really looks trivial, and it is hard to believe that this will be helpful eventually. But it will, and you will see in the next video and the followings how helpful it will be. The second says that if we multiply an equation, the whole of it, for a scalar different from 0, then again, this will not affect the set of the solutions of the system. Here, in this picture, we are multiplying the blue equation, the second one, by alpha, which we are assuming to be non-zero. As you can see, that means that every coefficient of the equation has been multiplied by alpha. So we have alpha x instead of x, minus alpha y instead of y, and alpha 7 instead of 7 on the right side of the equality. The last property of the three is the most complicated. We replace one equation with the sum of itself plus a multiple of the second one. Here, we replace the red equation with a sum of the red equation plus alpha times the blue one. This is why we have 2x plus alpha times x, then 3y minus alpha times y, and on the right side of the equality, minus 1 plus alpha times 7. In summary, what we did is red equation plus alpha times blue equation. Let's apply the last formula, which is the most complicated, to our first example, just to make things clear in an easy way. We observe that if we want to eliminate the variable x from the red equation, the first one, then we need to subtract 2x. This is what we do. We apply the previous rule by doing red equation plus minus 2 times blue equation. And we replace the red equation with the result of the last operation. Then we are simply copying the blue equation at the bottom of the system. We are not touching it. So now finally you can see that here you have 2x minus 2x, and we can cancel them. Here you have 3y minus 2y. That means 3y plus 2y, which is equal to 5y. And on the other side of the equality, we have minus 1 plus minus 2 times 7. That means minus 14, which is equal to minus 15. Now, let's rewrite those computations in a nicer way. As we saw, the upper equation is now 5y equal to minus 15. And exactly like before, we obtain y equal to minus 3. And repeating the same computations as before, we recover the value of x, which is 4, as you remember from before. Exactly the same computations. Again, the solution of the system is x equal to 4 and y equal to minus 3. But we used a complicated way to get to it. In the next video, we will see how to transform a system of linear equations into operations between matrices, and how those three operations that we just described will actually save our life when we'll have to study harder linear systems than the small one we just saw today. So that's it for today, but stay tuned. I'll see you in the next video. Thank you very much for watching. Please don't forget to like, comment, and subscribe. Thank you very much again. Bye.